Hello everyone, welcome back to our computer graphics series. Today we are tackling a fundamental concept that makes everything you see on the computer screen possible: window to viewport transformation. If you ever wondered how a massive game would world or a detailed computer-aided drawing gets mapped into a specific monitor resolution, this is the math behind the magic. Let's dive in and see what really happens there. First, we need to define our two main players, the window and the viewport. The window exists in the world coordinate system. Think of this as a computer lens looking at your infinite game world. It defines what you want to see. Second one, the viewport. The viewport exists in the device coordinate system, basically your physical screen. It defines where on that screen the image will actually appear. So transformation is simply the process of mapping what's inside the window to the area defined by the viewport. To see where this fits in the bigger picture, let's look at the pipeline. We start with the object space, defining our modules. Then we move to the workspace, arranging them in a space. Then comes the window. We clip away everything outside of this frame. And finally, viewport mapping. This is crucial step where we mathematically transform that window contents into pixel coordinate for your screen. Let's look at the geometry. We have point P with coordinates xw, yw inside a window. We want to find its corresponding positions. Let's say P dash with coordinates xv, yv inside the viewport. Both the window and viewport are defined by their maximum and minimum x and y values. Basically, it's their bottom left and the top right corners. Our goal is to calculate the new coordinate system while keeping the point's relative position exactly the same. The first step is figuring out the scaling factors, or how much we need to shrink or expand the image to show in the screen. So we calculate Sx, which is the scaling factor for x, and Sy, which is the scaling factor for y. Ideally, this is just the ratio of viewport's width to the window's width. If the viewport is half the size of the window, our scaling factor is 0.5. Now, for the actual formula to define the new xv and yv, we do a three-step logic. One, translate the window points to the origin, which is subtract xw minimum. Second, scale it using our scaling factor Sx or Sy of our choice. Third, translate it back to viewport's position, which is adding xv minimum. This formula ensures that if a point is 50% on the way across the window, it ends up exactly 50% of the way across the viewport. So let's try a quick example to prove how it's work. Imagine a window from 0 to 100 and a viewport from 50 to 100. We have a point P at 50, 50 exactly in the center of the window. First, we calculate the scaling factor. Since the viewport is half the size, our scale is 0.5. Plugging it into the formula, we get 25. So our new point is 25, 25. This makes a perfect sense. It is exactly in the center of the viewport, just like it was in the window. One critical thing is watch out for is distortion in these cases. If our scaling factor Sx and Sy are equal, we have a uniform scaling. This actually means that the objects keep its proportions. But if Sx is not equals to Sy, we get a distortion. As we can see in the right hand side of the screen, a circle in the window might get squashed into an oval if the viewport's aspect ratio doesn't match the windows. Why is this useful beyond just drawing things? It gives a powerful tools. First one, zooming. By simply making the window smaller while keeping the viewport the same, we map a smaller area to the full screen, which creates a zoom effect. Second, panning. By changing the window's position, which is moving minimum and maximum values without changing its size, we can scan across the world, creating a panning areas. So let's wrap up the things. First one, the window is what you see in the world. The viewport is where it goes on the screen. Second, the formula involves translating, scaling, and translating again, which we have already seen. Third, the scaling factor is just the ratio of two sizes, the window size and the viewport size. And finally, mastering this allows for features like zooming and panning that covers the window to viewport transformation. I hope this cleared up the math behind the graphics, and next time when you see your game loading, you have less confusions of what's happening behind the screen. So if you have any problems, leave them in comments below. Don't forget to like and subscribe for more computer graphics tutorials. Thanks for watching.